Thank you. It's my first time to be in India, so everything is new for me. Thank you for inviting me to be here. They gave me a lot of work. I have to speak 3 times plus another lecture. But it's with fun that I do this. So I'm trying to go and tell a story over these 3 hours. I cannot go a lot in detail, but there is a manuscript here. And what is not there, most of it is not there. But for those who are interested, I base my talks mainly on this group, on these books. There are 2 volumes, volume 1 and volume 2. And it's a funny title, Group, Ring, Groups, but if you think about it and you're smart enough, you know what it means. You know what a group is, you know what a ring is, and you can make a group ring, I will explain. And once you have a group ring, you can make groups in the group ring. So we only use 3 words to say a lot, so I feel smart already now. If you really want to sleep very well, buy those books, read a page every night, and you're guaranteed very well sleep, right? So what I do as a mathematician is, I told the story during lunch also, Amitsur is for me a big example, and Hurstin also. And Amitsur said, okay, in mathematics we prove lots of theorems. We're trained in school and university to prove theorems, and we prove if this and this holds, then prove this and this and this. Fantastic. And the worst the professor can ask you, give me an example of this, and students panic, because it's much harder than proving theorems, in my opinion. But Amitsur said, I want to know when the if is satisfied. For example, if you say, take a matrix ring, okay, you say, I take a matrix, this looks an array of numbers. But if I give you a ring and I tell you it's a matrix ring, and I ask you, prove me it's a matrix ring, that's not easy. And some of these problems will occur also here. Another thing that I really liked is Hurstin. If you asked Hurstin, why do you do this? And his answer was always, because it's fun. So if you don't find it fun, please go home and do something else. There's other things to do. So the main thing for me is also fun. Okay, so let me start with the definitions. Is there anybody who doesn't know what a group ring is here? And please raise your hand if you don't, because otherwise I assume you know it. Lucas doesn't know it, okay. Everybody knows what group rings are. So then I just introduce the notation. So R is a ring, G is a group, and in almost everything I do, I assume it's a finite group. And then I write the group ring, RG. Sometimes I might write brackets, and I don't know if I will be consistent. Sometimes I might write this. And it's the set of formal sums, but if you know module theory, is the free R module with basis G. So that means elements look like this, where all RGs are in the ring. And you know how to add them. You add them components-wise. And now I'm going to go to this group ring. I want to make from this ring and a group ring. So I want to multiply, and I first should multiply 2 such elements. While this is in the ring, you can multiply in the ring. And these are in the group. So you multiply them in the group, and you get a new element. And you extend this in a distributive way. That's your group ring. Okay. So basically, it depends on your of what you like in mathematics. If you like ring theory, I prefer this ring than the group. Because I know a bit more ring theory than group theory. If you don't like ring theory, then you prefer to go to the group probably to know something about the rings. Okay. There is also an augmentation mapping. And I use the notation that Angel is using, which I do not like, but I will use it anyway now. So with a group ring element, you associate the sum of the coefficients. And that's a ring homomorphism. Okay, that will be relevant very soon. You could also have, if n is a normal subgroup of G, then you could, sometimes I denote this as G, and you could also do this, and this is the relative morphism. You go from Rg to Rg over n. Where you do the same, but you take things modulo the classes. So Rgg goes to some Rg Gn. If you take n equal to G, you get the first mapping back. Sometimes I might add here that it's over R, so I might do this here sometimes. But I don't think I will use it a lot. Then there is the kernel of this morphism. I'll write it for Gn. This is this. And because n is normal, it's the same as this sum. Okay. This has to do with the following element, and I need that notation. N tilde is the sum of the elements in n. Okay. And this thing here you can see is equal to the annihilator in Rg of n tilde. It's easy to verify. Now n tilde, this will be important later. If I multiply n tilde with n, you just get n back, n tilde back. Right? If I therefore square it, I get the order of n times n tilde. In other words, n tilde is almost an idempotent. So a thing in square that is almost itself up to a scale you call an almost idempotent. And you can make it into an idempotent as long as you can invert the elements of the group. So if you do this, if you're allowed to do this, so if the order of n is invertible in the ring, now you can talk about this. And this we usually denote by n hat. So this is an idempotent. So in other words, in group rings, it's very easy to construct idempotents if you know subgroups. Useful for later. And you can decompose your ring, assuming that 1 over n lives in the ring, as Rg n hat plus Rg 1 minus n hat. And this is isomorphic to R, the grouping of G over n plus, right here, Rg. So you see natural epimorphic images of G, its group ring appears as the direct factor of what is here. Okay. Now the title is group ring group, so I want to go to groups in group rings. So therefore I will use the following notation. U of R is the group of invertible elements in R. I probably wrote too high here. That's the unit group, or group of invertible elements. Okay. Now you see under the augmentation mapping, if I would go from ZG to Z under the augmentation mapping, then what happens with the unit? The sum of its elements must be an invertible element on the ring homomorphism. These are only two, that's plus or minus 1. So therefore, the augmentation of U is plus or minus 1. Here I work with Z. So therefore, all units of ZG are, you take those of augmentation 1, I denote them with U1 of ZG to be suggestive, and there's plus or minus. In Angelstok, this will be VZG denoted. But in the book, you see the notation U of 1. Another thing that I need before I can go to the real things is an involution. And this will be the classical involution. If R is a commutative ring, you can do this. G is my group. Then you have an involution star that does this. This is an involution, so it's an anti-isomorphism. Okay. Now, what is the idea of a group ring originally? If you want to go from group theory to, so this is groups, to ring theory, then you should put the minimal possible information, and if you work in characteristic 0, the integral group ring is the most natural object to consider. And then you might naively think, or maybe optimistically think, I convert from group theory to ring theory, and this should contain all the information to determine the group. So if you do that, then you would like this to be true. The isomorphism problem for integral group rings, it says if ZG as a ring is isomorphic to ZH, if to go from group to ring theory and back should work well, then you would like the G is isomorphic to H. That's the isomorphism problem. If that philosophy works well, then you basically convert group theory to ring theory. Okay, I'll come back to that later. Well, it's not a question mark anymore, but I'll come back to that later. Now, well, I said I started looking at units. You might think, well, you could convert this problem into, how does it relate to this? As groups, isomorphic. Are the groups isomorphic? Call this isoprime. You should think a bit of examples. In general, if two rings are isomorphic, well, then their unit groups are isomorphic. But in general, an isomorphism type of a ring is not determined by the invertible elements. An easy example, but this is an infinite case. Take a polynomial ring in one variable over a field. What are the invertible elements? These are the non-zero constant terms. If I take it in two variables, still the same. So there's no way, and if you do it over Laurent group rings, they allow the inverses also, you don't distinct these infinite groups at that moment. But this is finite. So, but in general, to go from rings to assume that the unit groups determine the information is far from true. Here it is true. And it's sad to admit, but I only realized this since last year. So it's the first thing you should know. Last year, a PhD student of mine was working on this, and then we were together with Angel and Pavel Zalisky asked us a question. Well, you know, if you know something here, what's the relationship? And so, this is impossible that this is equivalent. And I remember in the old days, people say, we want to do unit groups because it's somehow important. It is really equivalent. That already says that the integral group ring is a special ring, somehow. Let me try to explain you how to prove this. If you know enough results in group rings, this is not difficult. And one of the lemmas you have to know is the following, and Angel will most likely prove this, or the first one at least. So this is lemma 0.1. So G is a finite group. And then the following conditions hold. The first one is an old result of Berman. And it says the following. If you have a unit that is a unit in U1ZG such that of finite order. So power of it is 1. Such that the coefficient of 1 is not 0. Well, then this unit is 1. So the linear combination with sum of all the coefficients equal to 1, if that is a unit of finite order, so there exists an n, so that alpha to the n is 1. And if the coefficient of 1 is not 0, then the element is already 1. Most likely in Angel's lecture this will be proven. Okay, if you have this, then you can also prove the following. If H is a subgroup, H a finite subgroup of U1ZG, I wrote something wrong in my notes here, I see. Then H is independent. And I can talk here about Q independence because I can consider ZG as a subring of QG, and that's a vector space. So I can talk about Q independence. So they are independent. And of course, if I consider ZG as a subring of QG, the dimension of QG is equal to the order of G. So if I have an independent subset, its size must be less than the dimension. So in particular, so if you have a finite subgroup in the augmented units, then it is at most of size G. This follows very easily from this one, with a bit of work. Not a lot, but a bit. Okay. And then the third one, I'll write that here. If H happens to be equal to G, then the Z linear combinations of H is the same as the Z linear combinations of G in ZG. Okay. So here I consider the group ring ZG. H lives there. I take the Z linear combinations. They're independent, it was written. Then you get a full ring. Okay, the proofs are in the notes, and maybe Angel talks more about this. Okay, let's now see why these problems are equivalent. So proposition, G and H finite groups. And the following are equivalent. First of all, ZG is isomorphic to ZH, and this is the ring isomorphism. G and H, yes, thanks. Second one is U1 of ZG is isomorphic to U1 of ZH. Of course, now you have to be a bit careful. This is the augmented units, those of augmentation 1 in ZG. And I consider the grouping ZH, and I take those of augmentation 1. These two groups are isomorphic. And thirdly, and this is a group isomorphism. And thirdly, U of ZG is isomorphic to U of ZH. And of course, this is again a group isomorphism. So that would prove that iso and iso prime are the same. Now, some things are obvious. This is obvious. Okay, and let me see what else is obvious. This, we have to do a little bit of work, and I'll explain it, and then we have to prove this. Okay. So let's see, well, that 3 implies 2. This is a classical trick. You have somehow to augment your isomorphism. So you start here with an isomorphism, which I denoted F, between the unit groups. Isomorphism, and I now want to go to an isomorphism that preserves augmentations. And so what you do is you have to change this isomorphic, I call it an F star, and this is the classical formula. Again, I wrote a typo here, I see. So what you do is sum of the ZG, G, you map onto sum of the G, what is it, ZG, and then the augmentation with respect to H of F of G. You take the inverse, and you take F of G. So here F of G lives in ZH. You have an augmentation map with basis H. You take its augmentation mapping. Since G is a unit, this is a unit, so its augmentation is not 0, so you can invert it. And then you multiply with this, and you verify that this is an isomorphism. That preserves augmentations. So something of augmentation 1 goes to something of augmentation 1. Easily verified. Which means that you proved that 3 implies 2. Okay. Okay, then remains 2 implies 1. And if you come from ring theory, as I said before, your first reaction should be, you must be nuts. If the groups are isomorphic, the unit groups, why would the rings be isomorphic? So this is special here. Let me show you. So assume you have an isomorphism that preserves the augmentation. Okay. Now F of H lives here because H is a group. It's invertible. So F of H, of course, lives there. I should go, I wrote it down in the other direction. Let me do it the same. So I take just the image of this H, I get here, I get a subgroup there. This is finite. And by the lemma here, its order is bounded by the order of the other group. So from the lemma, you get that the order of FH, it's a finite subgroup here, is bounded by the order of this group. Right? Now reverse the arrows. So similarly, of course, this is the order of H, because there is an isomorphism. You get that the order of G is smaller equal than the order of H. So G has the same order as H. Okay. But if G and H have the same order, then you look at the Z linear combinations of FH. That's a group of order H and a group of order G, in other words. What is this equal to? These elements are independent. This is a free Z module of the same dimension as this free Z module. And then you get that this is equal. Otherwise, you go to the rational group algebra and you see that you have a contradiction. And if this is equal, then it follows easily that the mapping F from ZH to ZG, where you extend what happens to H to here that it is an iso. Okay. So for me, it's pretty remarkable that this is true. And for somehow, now I finally have a very good motivation why the unit group is really relevant, if you're interested in the isomorphism problem. Okay. That's not even in those two books. It's not in the paper, it's in the thesis of my students. He wrote it in the introduction of his thesis because when we discovered this, I said, you know, people should know. And many people don't, I think. Well, I didn't, at least. So his name is, if you look at the thesis on the internet, Temmerman. Dorian Temmerman. Okay. So, okay, unit groups are relevant. So therefore, you would like, for example, to know, I would state a problem here. It's always good to have problems. What about the following? Suppose G is a finite group. And the question is, does there exist a torsion-free normal subgroup I think I gave it a name, N, say N, of U1ZG, such that I can rewrite U1ZG as a semi-direct product of N and G. In fancy language, this is the same as saying that what is it? I'll try to not make mistakes. This injection splits by torsion-free thing. Why does one ask this question? If you have an answer, a positive answer to this, it's easy to prove, it's maybe a good exercise, to prove that the isomorphism problem is true. So if you have this, iso follows. So that's a good reason to do this. Now, it's stated here, an affirmative answer has been given. For example, if G is an idempotent group. No, but I'm saying something completely, forget that. An affirmative answer to iso is given for G finite nilpotent. This is Scott a long time ago. But this is not proved this way. I mean, it's a fantastic proof, but for me, it's still a black box. If I would be able to do this and construct this N, it's not a black box anymore. So the question is this true for nilpotent groups? It's open. And a sub-problem is, this is a problem in Segal's book, even for nilpotent class 3, it's not known. Nilpotent class 2, it's true. But nilpotent class 3, it's not known. So even that is very specific and, in my opinion, interesting. For those to advertise my 4th lecture, maybe I will talk about that a little bit. Via braces, one gets closer and closer to this. And braces are solutions of the Young-Baxter equation, which looks like, what the heck, right? But since that's also fun, I should advertise that. But anyway. I mentioned several positive contributions to the this result. There's old results of, for example, for finite abelian groups, it's very easy. And for finite abelian groups, it follows from this lemma von Berman directly. There are some other classes of groups for which it's known, but I leave that to you to read because my time is running, I see. Okay. Okay, so I gave some basically motivation why to look at unit groups. Okay, now that you're potentially interested in unit groups, okay, it's a bit funny because what you do is you start with a small group, and small means finite, and then I blow it up to U Z G. Okay, it's fine to talk about it. Can you construct me units? Show me the money, show me units. And maybe you discover that this is an immense group, and then you might say, wow, this is ridiculous. You make from something very small, very big, and now you want a small back. That's the isomorphism problem. But I maybe convinced you that units are relevant, so we have to go to constructions of units to see they exist. If you can prove they're only elements of G, well, then it's easy, of course. But, so constructions of units. And there are some exercises at the end of this section is, I think anybody who starts or is interested in unit groups or integral group rings should start with calculating examples. Take your smallest favorite group. Of course, you could take the trivial group and then it's a bit easy. But you could take C2, the cyclic group of order 2. You should do this. Take C3, you should do this. C4 should do this. This is pretty easy still. C5 should do this, not so easy anymore. Now you go to groups of order 6. Everything I know about units, I claim this to everybody, is because I know ZC6. Or ZS3, I should say, probably. So, but you should compute that. Now people can do it all kinds of ways, but you should compute it and try to compute a full unit group. But before you do that, you should at least know some constructions of units, otherwise it's very boring, right? And it's funny that the research in unit groups didn't start this way. People proved fantastic results. And if you ask them, show me units, they say, oh, we don't know. Which is funny. Yeah? So how big are unit groups? So let me give you some constructions. We basically know only 2, apart from the trivial ones. These are very boring. These are the elements, plus or minus the elements of G. We call them all trivial. So trivial doesn't mean the group is trivial. It means these are the obvious units. Okay? Then there are special units, unipotent units. And they lead to bicyclic units, and I want to explain you this. And then there is a third class, which are the cyclotomic units. And they lead to bus units. So basically, I give you 2 constructions. And actually, if we're really honest about it, we don't know any others, more or less. But we can do a lot with that, which is also amazing. Okay, so let me try to explain you unipotent units. Unipotent units means something 1 plus a nilpotent. So for example, if I would take a nilpotent element, say 1 plus alpha, and alpha squared is equal to 0, then this is invertible. 1 plus alpha inverse is 1 minus alpha. If I take a unipotent unit, say of nilpotency class K, then I can do something like this. And I hope I don't make mistakes. I believe this is 1, and they commute with each other. So I've constructed a unit, right? But I'm cheating. I say, take a nilpotent, so therefore I've constructed, well, show me now nilpotent elements, right? So let's try to construct nilpotent elements. Well, one can construct nilpotent elements from idempotents. Of course, then you might say, give me idempotents, but I will give you easily idempotents. Okay, so let's say this is an idempotent E. It means E squared is equal to E. And then I can do 1 minus E times something in the group ring times E. If you square this, what do you get? You square this and you put this after the E, and E times 1 minus E is 0. So the square is 0. Hence, I've constructed units. And these are units of the integral group ring. I could have done this also with almost idempotence, say that E is an almost idempotent. Which means that E squared is an integral multiple of E. Let's say a positive integral, and now you take this element, n minus E alpha E. And now you calculate n minus E times E, and you see that you get 0 because of this. So the square of this is 0. So you also have units 1 plus n minus E alpha E is a unit. Okay, I should see. Yeah, thanks. It seems that I'm shifting always the problem to new elements. So let's now construct idempotence. But I've given you idempotence before. The hat of a subgroup. So if I take a subgroup of G, and I form the hat, which was this. This is an idempotent. So if you have the lattice of the subgroups, you have many idempotents. Of course, you might say, but you cheat, because does this live in ZG? No way, except if the group is trivial. That's why I also mentioned the almost idempotence. This is an almost idempotent. With those, I can construct units. Okay, so let me now introduce some notation. You could also wonder, well, let's do this first. Okay, so I've introduced B, H, E. This is an idempotent. And this element, H, I take in G. And by definition, it's this element. There is this mysterious NE. NE, I take the smallest positive integer such that NEE belongs to ZG. What am I doing here? You can prove with exercise, but maybe not so easy. Are there idempotents in ZG? And you can prove that the only idempotents in ZG are 0 and 1. There is a result that says the coefficient of 1, if you express an element in the group ring of an idempotent, lies between 0 and 1 if you take the element as a rational group ring element. So they don't exist. That's why I look for idempotents in QG. And of course, any element of QG I can map with an integer back into the integers. Okay. And this is called a unit. I can, of course, do similarly B, E, H. And you see the E is at the side where it's right or left here. That's also a unit. And we give these children a name. We call them generalized bicyclic units. H is an arbitrary element of G, of the group. And for a generalized bicyclic unit, I need an element of the group, and I need an idempotent in the rational group algebra. Okay. Of course, you should be a bit careful because you say, okay, you construct units, but maybe this is 1. Maybe this is 0. Good question. if I would take this idempotent for E, when does this become 0? Exactly when H is the normal subgroup, when this little h normalizes this. So 1 plus, let me use other notation, H, no G, H hat, 1 minus H hat. When is this equal to 1? Exactly when G normalizes H. So for example, in the abelian case, I've constructed nothing. Yeah? But if you have subgroups that are not normal, then you construct now really real units. And this is already interesting because you might wonder, well, you construct a new unit, but maybe it's again of finite order. But if you think of an element of this form, and these elements are of that form, if I take powers of this, what do we get? Hint for the students to make them nervous, it's completely trivial. You use the binomial of Newton, but many things are 0. So you get 1 plus k alpha. If alpha is not 0, then this is not 0 in the integral group ring. Right? What does it mean about these things? So if alpha is not 0, then 1 plus alpha has infinite order. No power is 1. So I've constructed infinitely many units, which says it's already different from my original group at least. Okay? One more notation, B, H, G tilde, which is the notation for B, H of this group. And I should define it, is 1 plus 1 minus G, H, G tilde. And B, G tilde H is B, H is 1 plus G tilde H, 1 minus G. These are called the bicyclic units. Okay, so remember these. And these look very similar, but one is built on an idempotent, the other one on an almost idempotent, although smart people would say, well, this is not 1 minus n order of G, but this is a multiple. If you look at 1 minus G hat, this contains, what is it? 1 minus G hat times 1 minus G is equal to 1 minus G. So 1 minus G is a multiple of this. So, okay. And then with a bit of calculations, you see that the one group sits in the other one. Okay, but these are important, the bicyclic units, the bus units. So that's one type of constructions that I've given you, and I want to give the other one here. But maybe I should also tell you the following. Why the heck does anybody come up with this idea? And that's why ZS3 is also interesting. I'll come back to that next time. You look at the Wedderburn decomposition of QS3, and some matrices show up. And matrices are very good rings to work with. So for example, I take M2Z. Construct me idempotents. You know, the obvious ones. E11, 1 on the one spot and 0s elsewhere. That's an idempotent. This is not a central idempotent. I can use that for that thing. I could also have used E22. And E22 is 1 minus E11. So if I do this construction, what do I get? Some matrix here, and here E11, and then 1 plus this. What type of matrix is this? This is E22. This is a lower triangular matrix. This is something like this. row-column operations, right? So for me, when I think of bicyclic units, they're upper and lower triangular matrices in my head. Not always completely correct, but we'll show later a lemma that this is a good philosophy. Okay? And now you see from idempotence you construct things. Okay, the third thing is bus units. And I see that I go much slower than I thought, but anyway. So what do we do here? So I now go for the bus units and the cyclotomic units. And this looks a bit more complicated, but you can do this in an arbitrary ring. So R is a ring, X is a unit of R, and X is finite order. Say X to the N, I think I used X to the N is 1. So if you work in the group ring, you take an element of the group that plays this role. Okay? And I do this thing. And I take here K, a positive integer is relatively prime with N, the order of N. That's the first thing I do. If you think of your analysis classes, you see this stuff showing up. But if in analysis, this might be a root of unity. If you then multiply with 1 minus x, or at least if you do this up to n minus 1, and then you do times 1 minus x, you get 0. So it cannot be a unit. So this is in general not a unit, so you have to fix it. So how does one fix it? One takes a power, m, and the power one can choose, for example, is such that k to the m is congruent to 1 mod n. And then I have to add a term to get it back into shape I want. And this we denote with u, k, m of x. If you use representation theory, for all representation, if this would be in a cyclic, generates a cyclic group, in all the representations, this becomes a unit, except in the trivial representation. And that's why this is a fixing factor. But I could also, and it's in the notes, give you the explicit formula for the inverse and you calculate it. But that's boring and not instructive. But once we know Wedderburn decomposition, much easier to prove that it's a unit. If you would work in number theory, if you would work with the ZXCN, and C is a primitive nth root of unity, the complexes, you take the Z linear combinations, and I take now for X this C to the N, then this thing is 0. Multiply it with 1 minus X, so you get 0. So one of the factors has to be 0 because I work in a domain, and this has to be 0. So what is left here, this piece becomes 1 minus X to the, well, 1 minus C N to the K divided by 1 minus C N, and there we have taken that exponent M. Such a unit, such a thing, you can prove that it's inverse, and it's inverse, you know what it is, you should flip it over. You have to prove that it still lives here, which is not so difficult to see. These are called cyclotomic units in ZXC. Okay. So in some sense, I'm imitating cyclotomic units. Well, I'm not doing this. Bas invented this. Okay. There are some formulas that you can read in the notes. But if I start with the integral group ring with G a finite group, and I take all the U, K, M with X replaced by G, 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 these are called the bus units. They give you units. The only thing I've used is the integral group ring of the cyclic group. Oops, of the cyclic group. So I get units here. Here the k could be any positive integer relatively prime at n. You can restrict it to numbers smaller than n by checking some formulas. Now, why are the bus units or the cyclotomic units useful? The following result tells you that. That's a theorem, an old theorem. So C, a complex root of unity of order n. Then the cyclotomic units generate a subgroup of finite index in U of ZC. And with the results next time about the Weatherbund decompositions, this might indicate that you maybe get such a result for groupings of cyclic groups. Okay. I have to finish. Let me write one more down to indicate you why the bicyclics are useful. And I told you the matrices are useful, so I will write it in that context. So here's a proposition. The group, maybe it's a bit exotic at the moment, SLNZ, is generated by the matrices Eij, which is 1 plus Eij's, with I different from j. So somehow, as I told you before, for me these are bicyclics in matrices. Then there is a famous result of Sanov, and it tells you something special. If I take matrices of this type, E12 Z1 and E121 Z2, and what do I mean by this? This is 1 plus Z1 times E12, and this is 1 plus Z2 E21. You take the group generated by these with Z1 and Z2 complex numbers such that the modulus of Z1, Z2 is larger or equal than 4. For example, take them both equal to 2, the number 2. This is a free group of rank 2. Okay, interesting to know. And then finally, the third one is, if I look at this group, I'll do it again with 2 by 2 matrices in SL2Z, so determinant 1, and A is congruent to D is congruent to 1 mod 4. So I like to think of this group as 1 plus 4Z, Z, 1 plus 4Z, Z, I hope I don't make mistakes, and those of determinant 1 that visualize what I'm doing. That's a free group of rank 2, and it's generated by these two matrices. Why do I say this? Well, it's free, that's one relevance. This group is very large in SL2Z. It's a finite index. So I've created with bicyclic units a very large subgroup of SL2Z. I've created with bicyclic elements the whole of SLNZ. So one could imagine going a little bit deeper in here, it may be still relevant there. And next time I will show you some theorems that this is indeed the case and that these two things generate a lot. But also these results are relevant to say, now if you have such matrices in your group ring, then you have very large groups because you have free groups. And free groups are immense in some sense. So you have lots of units. So then to come back to the original thing, you start from a small group G, I make a massive ring ZG, I get lots of units, and I hope that I rediscover this very small group. Bizarre idea. But if you think of the problem 3 that I posed, if you have a torsion-free normal complement, that means I'm looking for a very large torsion-free subgroup. This is what the bus and the bicyclics hopefully do. I factor it out, and if you're very lucky, there is your finite group. Can you do this for nilpotency class 3? If you can do that, I give you a PhD. If you don't do this, I give you maybe a PhD for something else. Okay, that's it. I already sent it to Suganda, so they might not be completed, but maybe it's best to send them out to, or put them on the web, and I might make some changes later here and there because I noticed some typos while I was here. Sure.
The last thing you wrote E1 to Z, E1.
True. So these matrices, and if you visualize them, it's 1, 2, 0, 1, and 1, 0, 2, 1. Many people prove in the first time to do a group theory course, they construct free groups in a very abstract way with words. And when I was a student, I always asked my professor, show me this stuff. Is this real? That's very real. That's a free group. To me, you should first give that and then do the abstraction. But that's my personal point of view. This stuff exists.